Hello everyone. Welcome to this webinar for 5G NR gNB transmitter conformance testing basics. My name is Peng Yao, application engineer from HFM COE of Keysight Technologies. In the next 1 hour time, we will discuss the base station transmitter conformance testing requirements and show the best practice with some example measurement results and demos. The agenda for today's webinar is like this. We will start from a quick overview on 3GPP conformance test specifications, the typical transmitter test setup, and also test models. Then we move to the major part to introduce the conformance test items, requirements, and measurement examples. At last, we will have a short Q&A session. At the beginning, let's take a quick look at what specifications define the conformance test requirements, configurations, and procedures. 3GPP Run 4 working group is responsible for defining base station conformance test. The minimum RF requirements can be found in 38.104, while the corresponding test configurations and method for each item are in 38.141. Similarly, Working Group Run 5 defines the conformance test specifications for UE side. It's critical for every 5G NR base station or UE manufacturer to pass all of these tests before releasing their products to the market. Otherwise, the product can't be recognized as 3GPP compliant. Therefore, can't be used for network deployment. In this webinar, we will focus on the conducted transmitter test for FR1 base station by going through the transmitter test items, requirements, and method in document 141-1. In addition, with the example test results from Keysight 5G NR measurement application running on a spectrum analyzer, I believe you will have more impression on how the tests are performed in an efficient way. One message to share with you: a follow-up advanced session is being planned to cover the radiated testing and some advanced topics, so please pay attention to the invitation from Keysight Technologies. The test setup for transmitter test is relatively simple, where the RF output signal from gNB is firstly attenuated and then connected to the spectrum analyzer in a conducted manner. Because the maximum output power from gNB could be more than 40 dBm, that already exceeds the maximum allowed input power of the instrument. So the attenuator is needed here to protect the instrument, and the attenuation can be mathematically compensated by the measurement application. In addition, 10 MHz reference and the frame trigger from gNB are also connected to the instrument. Interfering signal is required for intermodulation test, where it's generated from a separate signal generator and then input to the transmitter through a circulator. This is represented by the dotted lines in the setup. To have a full coverage on transmitter test, 5G NR measurement application running on the instrument should have the capability for all of these test items. Channel power and occupied bandwidth. These are the very basic measurements for signal power and bandwidth. ACLR, OBUE, spurious emission. These 3 items are all for unwanted emission test, but target for different frequency offsets. ACLR for adjacent channel, OBUE for operating band, and spurious for out-of-band emissions. Transmit on-off power. This is specially for the TDD signal. EVM frequency offset, and timing alignment error. These three items belong to the modulation analysis that can get the gNB signal demodulated with the corresponding test model, and then report various measurement results. Okay, we just mentioned the test model for signal demodulation. Then what is test model and how it's used in the transmitter test? Let's talk about more. Generally, test model is a set of signal configurations that are well defined by 3GPP for gNB transmitter test. Each test model is used for a particular test item. It includes the general configurations like cyclic prefix, maximum RB number, TDD frame structure, as well as the specific channel settings. There is no SSB included in the test model, only control channel and data channel. The resource allocation for each channel is defined in terms of symbol number and location in the time domain, and RB number and location in the frequency domain. In next slide, we will use test model 3.1 as the example to show the resource allocation in a graphical display. In addition, power level, DRMS type and location, modulation level, and data content are also the key channel profiles. More importantly, test model definition keeps evolving in each release of 3GPP test spec. For example, recent changes in March version include using PN23 and the data content, and the new test model for NB-IoT operation in NR in-band test. So all of these changes require the measurement application always keep updated with the latest spec version. One thing I want to mention here, channel coding is not enabled in test model signals. Instead, just the scrambled PN sequence is used as the data content. So if someone wants to analyze this signal with 5G NR XApp, it can only be demodulated, but CRC for decoding will always fail. This table lists transmitter test items and the corresponding test models to be used for each item. Then, how test model looks like in terms of resource allocation in time and frequency domain. This figure takes test model 3.1 as the example and illustrates the resource allocated to each channel. This is a TDD frame structure signal, so we can see downlink transmission occurs at some slots and symbols, while the rest part in the frame is reserved for uplink transmission. The light blue part in each slot is PDCCH. PDCCH occupies the first two symbols in a slot and only has one CCE aggregation level that is actually 3 RBs in frequency domain. There are total 2 PDSH defined. The first one is the red part with RNTI2. It starts from symbol 2 and only has 3 RB allocated from the lowest RB in the carrier bandwidth. The second one with RNTI0 is represented by the big green part in the figure. It's located with all the available symbols in each slot. So for a full downlink slot, the last symbol is 13. But if it's a special slot, the last symbol is 5. In frequency domain, it's located with all the remaining RBs from 3 to 272. Other test models share same common settings with test model 3.1, but with different modulation type, power boosting, or RB number and location. For example, test model 2 only allocates single RB to each channel for EVM and the frequency error measurement. Okay, let's start to go through the transmitter test items and see what's the requirement and what test model is used. The first one is the output power. Please note that the test purpose here is not to measure the absolute level of maximum output power. Instead, it's required to measure the power accuracy relative to the base station's declared value when it's transmitting at the maximum power level. For example, 38 dBm for medium range base station or 24 dBm for local area base station. The test model used for output power test is test model 1.1, that the whole bandwidth is fully filled with the QPSK data channel. Here is an example of the real measurement result on 100 MHz bandwidth TDD signal of test model 1.1. Since this is a TDD signal, we will only need to measure the burst part within a frame. Otherwise, the measured result will be the average power that includes both burst and idle period. That is apparently not what we want to have, so we will need to configure the gate to only cover the flat part of the burst. From this screen, we can see the gate start and stop lines clearly indicate which part within a frame is used for the power measurement. The measured power result over 100 MHz bandwidth is minus 1.04 dBm, while the signal is transmitted at the declared value of 0 dBm. The cable loss is pre-calibrated, and we know it's about 0.64 dB. Then we can calculate the power accuracy is about minus 0.4 dB. So this accuracy level is within the requirement. Let's move to the next power measurement item, the output power dynamics, which means we will need to measure the power levels when base station is transmitting at maximum and minimum power levels, then calculate the difference between them. This difference value is called power dynamic and needs to meet the requirement in the table for different channel bandwidth and subcarrier spacings. When measuring max power, the test model of full RB allocation should be used. That is test model 3.1 or 3.1a, depending on if the base station can support 256 core modulation or not. While for minimum power measurement, test model 2 or test model 2a of single RB should be used. One thing we need to take care is the measurement should be done on the OFDM symbols that carries PDSH data only, meaning that no SSB or no DRMS within that symbol. If we continue to use channel power mode to measure the power dynamics, we have to specify the gate settings very carefully, because in the test models, there are also PDCCH symbols and PDSH DRMS symbols in a subframe. So we will have to filter out those symbols from the measured interval, and that would require very careful calculation on the symbol start time and length. Instead, a more efficient way is to use modulation analysis mode in 5G NR-XAB, where OSTP result is reported directly. OSTP is OFDM symbol transmit power, measured for date symbols only, exactly what we need in power dynamic measurement. Let's look at the example measurement result for power dynamic using the modulation analysis mode. This screen shows the measured OSTP result of minus 1 dBm for the maximum base station transmit power. It's measured with test model 3.1, which can be easily configured by selecting it from the test model list. After the signal is successfully demodulated, OSTP as well as some other measurement results will be reported. Similarly, we can measure the minimum power using test model 2 signal with single RB. Then, with maximum and minimum power all measured, it will be quite easy to calculate the power dynamic is about 25.48 dB. That is larger than the dynamic requirement. Transmit on-off power. This test only applies to TDD mode of the base station. Basically, there are two aspects need to be verified under this test item. The first one is to measure the power level when transmitter is off. The second one is to measure the transient time length, that is, the ramp up and ramp down time of a burst in the TDD signal. From the requirement table, we can see that the off power should be lower than about minus 83 dBm per megahertz, and the transient time should be less than 10 microseconds. Then let's talk about more how to make the measurement. First, off power is measured using a squared filter with the specified channel bandwidth or aggregated channel bandwidth for multi-carrier case. The measurement will be performed over a given time period when the transmitter is off, as the time average window should be centered between two bursts, with 10 microseconds as the guard period to each burst. The transient time is measured as the time period during which the transmitter can change from off power level to on power level, and vice versa. This figure is from 3GPP test specification, and I think it gives a very clear illustration about the relationship between transmitter on, off, and the transient period. We can see that transient period includes burst ramp up and ramp down parts that need to be measured separately. One thing you may be concerned about is the dynamic range challenge in transmitter on-off power test. That is, when base station is transmitting at the maximum power, the instrument's dynamic range is not sufficient for measuring on power and off power at the same time. To address this challenge, 5G NR-XF uses a special method called two-sweep to extend the dynamic range. This method sets a threshold power level to divide the power time trace into two parts, a higher power part and a lower power part. It first sweeps the higher power part with high attenuation and the preamplifier off to avoid the distortion. Then in the second sweep, it gets the lower power part trace data by optimizing the settings for low-level signal with minimum attenuation and the preamplifier on. Finally, the measurement application will automatically combine the solid lines in each sweep to provide the high dynamic range result. Now let's see the measurement example in 5G NR-XF for transmitter off power and the transient time. In this example, an external trigger is expected to determine the burst boundary. Then, by knowing the frame structure of the test model, the transient time can be measured with the detection of power ramp up and down. A power envelope mask is displayed to show the expected limit of off power and also the ramp up and ramp down positions. In the metric table at the bottom, we can see the measurement results include transmitter on power, off power, ramp up, and ramp down time. By default, the limits are set to the values from 3GPP spec, but it also provides the flexibility for user to further modify the limits for specific test purpose. Transmit signal quality. This is an important metric to show the quality of the transmitted signal, including 3 measurements: frequency error, modulation quality, that is also known as EVM, and time alignment error. Now let's explore more details for these 3 measurements. First, frequency error. This item is easy to understand. We will need to measure the actual transmit frequency and compare it with the assigned frequency. For a given test model signal, 5G NR-XF can achieve the synchronization with the known DRMS sequence. Then the frequency error will be measured by the internal estimation algorithm. The table at the bottom lists the requirements for different base station classes, depending on its coverage range. The second measurement is signal quality, that is usually expressed as EVM. When the test signal is demodulated, the measured data symbols can be displayed on the IQ constellation diagram. EVM is then calculated by the difference between the measured symbol position and the reference symbol position, which results in an error vector including phase error and magnitude error. This figure here shows the error vector for a single point, but the EVM required by conformance test is the RMS result, averaged over all the allocated subcarriers and all OFDM symbols. In addition, for different modulation levels from QPSK to 256 COM, there will be different test models used, and the corresponding requirements are also different, as shown in this table. When calculating EVM, some predefined settings for equalization, tracking, and windowing should be applied. This is usually called 3GPP conformance EVM. Both frequency error and EVM, and also some other metrics, can be measured by the modulation analysis mode in 5G NR-XF. There are 2 useful features: test model preset and one-button EVM optimization. They will make the work much easier for test engineers. So next, let's see a demo video of using 5G NR-XF to do the modulation analysis.
Hello everyone. In this video, I will give you a live demo of XF to show how the key features we just talked about can give the customer big convenience and fast measurement speed for conformance test. We can see under 5G NR mode, all the available measurements are shown here, and they will be used for different conformance test items. Let's start from modulation analysis for EVM measurement. The input signal is a test model 3.1 with 100 MHz bandwidth. So we just need to select the test model from the list and click apply. Then all the 3GPP channel profile for this test model will be automatically applied. We can further check the details of the channel profile as well as the graphical display for both time and frequency domain. When you select channel in the list, it will be highlighted in the graphics to show its resource location. This is quite useful for customers who want to confirm their understanding on each version of a 3GPP test model. Now we are able to make successful demodulation on this signal. Then how can we get the best EVM result? In the past, user has to adjust attenuation and IF gain separately to find the best combination of them. But now with one-button EVM optimization, everything can be done in just a few seconds. It's so easy that everyone loves this feature.
The third measurement is time alignment error, TAE. That is, the timing gap between different DRMS ports in the transmit signal should be smaller than a certain level. TAE test scenarios could be a MIMO transmission that multiple DRMS ports are used, or it could be the carrier aggregation case that the same DRMS port is transmitted in different component carriers, or it could be the combination of MIMO and carrier aggregation. Especially for MIMO case, the two DRMS ports will be from different RF channels, then combined together by a RF combiner, and finally input to the spectrum analyzer for TAE measurement. Then, depending on the test scenario, different TAE requirements should be applied. From the requirement table, we can see that for MIMO transmission, the timing alignment error should be less than 19 nanoseconds. Let's look at a TAE measurement result for MIMO configuration, where DRMS port 0 and port 1 from different RF channels are combined together. So this is actually a MISO case, that is, multiple input signals onto a single receiving antenna. We know that with only one receiving antenna, the combined two-layer signal can't be really demodulated. That is why some of the traces don't contain any data. For example, nothing in the IQ constellation diagram. In 5G NR-XF, when we select test model 1.1 with two layers, it can achieve the synchronization to each DRMS port in the combined signal, and then measure the timing error between them. So a single channel spectrum analyzer would be sufficient for measuring TAE. Let's take a close look. On a single input channel 1, both DRMS port 0 and port 1 are detected at a certain power level. Using port 0 as the reference, the timing error of port 1 is about 24 nanoseconds. In addition to TAE, we can see this measurement can also report the power gap and phase gap between different DRMS ports. Unwanted emissions consist of out-of-band emissions and spurious emissions according to ITU definitions. Out-of-band emissions are unwanted emissions immediately outside the channel bandwidth, resulting from the modulation process and the non-linearity in the transmitter. Spurious emissions are the emissions which are caused by the unwanted transmitter effects, such as harmonics, intermodulation product, and the frequency conversion product, but exclude out-of-band emissions. Furthermore, the out-of-band emissions requirement for base station transmitter is specified both in terms of adjacent channel leakage power ratio, ACLR, and operating band unwanted emissions, OBUE. Basically, they target for the emission impact to different frequency offsets. ACLR only focuses on the power leakage to its adjacent channel, while OBUE covers the whole operating band plus an offset at each side. This offset outside the band is defined as delta F OBUE, which depends on the selected operating band as shown in the table. OBUE defines a mask with a few segments to require the emission shall fall below that mask. So in 5G NR-XF, it's also called SEM measurement, spectrum emission mask. For the emissions that is even outside the frequency coverage of OBUE, the requirement for spurious emission will be applied. Specifically, it covers a wide frequency range from 9 kHz to 12.75 GHz, excluding the frequency range for OBUE. Let's start from ACLR. ACLR is to measure the power leakage to adjacent channels and expressed in the power ratio of the transmitted signal to the adjacent channel. The purpose for ACLR is to control the power leakage to adjacent channels under a certain level to reduce the interference. The transmitted signal could be single carrier or multi-carrier, and the requirements we discuss here will be applicable to both of them. This figure here shows a single carrier example with 4 different adjacent channel offsets. Offset A and B are for LTE carrier type, and C and D are for NR carrier. So we can see 3 key properties for defining the adjacent channel: frequency offset, integration bandwidth, and the carrier type. We will discuss in details in the next slide. This table lists the ACLR absolute basic limit for different base station classes and category, which means the measured absolute power in adjacent channel shall not be higher than the limit values. In addition to this absolute limit, there is also the ACLR limit, that is the relative power ratio. Base station is considered to pass the conformance test if it can meet either absolute limit or ACLR limit, whichever is less stringent. Regarding ACLR limit, the measured ACLR result shall be higher than the limit values per channel bandwidth in this table. There are a few points we want to talk about. First, 2 frequency offsets of the adjacent channels need to be measured. The first one, center-to-center offset, is equal to the base station channel bandwidth, and the second one is 2 times away of that. Second, the assumed carrier type in adjacent channel could be either 5G NR of the same bandwidth or 5 MHz E-ultra signal. So the frequency offset for adjacent channels and the filter bandwidth are determined by the selected carrier type. Last, the power measurement is centered on transmitted signal or the adjacent channels, using a squared filter with the bandwidth equal to transmission bandwidth configuration, that is BW config. For NR, it's calculated with the assigned RB number and the subcarrier spacing, while for E-ultra, it's using a fixed value of 4.5 MHz. For operation in non-contiguous spectrum or multiband case, ACLR will be measured on the adjacent channels inside subblock gap, where cumulative ACLR together with normal ACLR will be used as the limit for different channel offsets and subblock gap wise. Here is a graphical view of cumulative ACLR. Within the subblock gap, you can have both normal ACLR, where only one of the carriers, either the left one or the right one, can contribute to the subblock gap, or the cumulative ACLR, where both carriers can contribute. Depending on the carrier bandwidth at the subblock edge, the assumed adjacent channel could be 5 MHz NR or 20 MHz NR carrier. As a result, the offset of the adjacent channel will be also different. The offset inside the subblock gap is called inner offset. Take this 100 MHz carrier at subblock edge as the example. Inner offsets are 10 MHz for the first adjacent channel and 30 MHz for the second adjacent channel. Then we can see if subblock gap is larger than 80 MHz, all inner offsets are normal. If the gap is between 60 and 80 MHz, the first adjacent channel is normal. The second adjacent channel is cumulative. For gaps less than 60 MHz, either one or both offsets are cumulative. You may already notice there are many values in the table defining the offset, bandwidth, and limit for normal or cumulative ACLR. But don't worry, the measurement application will help you handle those complicated things in a simple way, not only for ACLR, but also for OBUE and spurious emissions that we will talk about later. Okay, now let's see a demo video of making ACLR measurements in 5G NR XF with the advanced preset feature.
Now let's move to power sweep measurement, for example, ACP. Similar to EVM, using preset is the easiest way to configure the measurement. So we just need to select test model 3.1 from the list and click apply. Since the input signal is a TDD signal, the sweep measurement can only be done over the burst part in a frame, so gate must be enabled. Here we can see test model preset already takes care of the gate settings to configure its offset and length accordingly. Gate view will show it clearly where the gate interval is located within a frame. If we look at the detailed parameters for ACP measurement, we will find it's not easy thing for user to configure it manually. Furthermore, these offset and limit values will get changed for different test conditions like frequency band, base station type and category, adjacent channel type. Fortunately, advanced preset manual will handle all of these complicated things properly. For example, we just need to select base station type 1C, category B medium range, and adjacent channel type for NR and E ultra, and click apply. All the settings will be applied accordingly in the behind, and we can go checking the measurement result directly. So this is exactly how XApp can help conformance test customers make easy configuration and fast measurement.
How does the gNB RF leakage impact the neighbor channels? The operating band unwanted emissions are defined to measure the out-of-channel emissions over the whole base station transmitter operating band, plus an additional offset of delta F OBUE on each side. These are the unwanted emissions resulting from the modulation process and non-linearity in the transmitter, but excluding spurious emissions. The green line in the figure represents the limit mask for OBUE, which covers the frequency range from channel edge to delta F OBUE outside the operating band. We can see the whole mask consists of a few segments on each side, where the start and stop point of each segment is defined by the offset from channel edge to the center of measurement filter. Two key properties are defined for each segment. The first one is the basic limit, which means unwanted emission within the segment must be under that limit. The second one is the bandwidth of the measurement filter. The basic limit and measurement bandwidth will get changed with the test conditions, resulting in a series of masks for different frequency band, base station type, class, and category. This will correspond to more than 10 limit masks just for FR1. But as we saw in the demo video, in 5G NR XApp, using advanced preset will provide big convenience for user to apply the wanted mask. For base station operation in non-contiguous spectrum or multiband case, it's similar to ACLR that the limit mask within subblock gap should be calculated as cumulative sum of adjacent subblocks on each side. This cumulative mask could have the cumulative region and the non-cumulative region. A stop frequency offset of 10.5 MHz is defined for the cumulative region, which means the region outside that point will use non-cumulative mask. Let's take this example to understand this. First, the limit contribution from the left subblock is spread into the gap area with a few segments. Then the same thing for the subblock on the right. Finally, depending on the location within the subblock, the cumulative mask will be calculated with the contributions from both subblocks. While for non-cumulative region, still the basic limit is applied. This time, we will see a measurement example of a 2cc signal with non-contiguous spectrum, which means the measurement will be done within the subblock gap, for example, 100 MHz. The measured trace is displayed in multiple segments, together with the blue line on the top, showing the limit mask within subblock gap. So we can see it actually includes the cumulative region with a stop frequency of 10.5 MHz, and also the non-cumulative region with a fixed limit value, which is pretty consistent with the 3GPP required mask we discussed in previous slide. The table below reports the worst point in each segment at both upper and the lower side, including the frequency location, power level, and the delta to limit. How will the emission of 5G NR signal possibly impact the other systems that are out of the operating band? Spurious emission is defined to measure the emissions across a much wider frequency range to make sure emission level is under the limit. Basically, the measurement region includes two parts. The first part is from 9 kHz to delta F OBUE below the operating band, and the second part is from delta F OBUE above the operating band to 12.75 GHz. For some operating band, if the fifth harmonic of the upper frequency edge is higher than 12.75 GHz, then the emission limit should also cover the fifth harmonic point. Regarding the emission limit, for category A base station, it's a fixed minus 13 dBm. For category B, the limit is minus 36 dBm below 1 GHz and minus 30 dBm above 1 GHz. Also, the measurement bandwidth will vary from 1K to 10K, 100K, and to 1 MHz, depending on the frequency location in the measurement region. Here we take band N78 as the example, where the frequency range is from 3.3 GHz to 3.8 GHz, According to the test requirement, the test model 1.1 signal will be transmitted at the bottom channel for measuring the frequency range below the band, while the top channel will be used for measuring above the band. There are total 4 ranges configured for measuring from 9 kHz to 3.26 GHz. The measured emission trace will be displayed together with the limit line for the selected range. In the bottom table, it will show the top 10 spurs detected for each frequency range, and the user can place a marker to the spur of interest to check its frequency and emission level. As long as all the measured points fall below the limit line, we can say this spurious emission test is passed. Otherwise, user can find those failed spurs in the table with the indicator of a red fail. Now let's take a look at the measurement setup. Total 4 frequency ranges are defined for measuring below the operating band, and each will have a specific measurement bandwidth as well as the pass-fail limit assigned. Range 5 and 6 are used for measuring above the operating band. Most of the parameters can be auto-configured by 5G NR-XF software, so user only need to make minor adjustments based on which band to be tested. The last item is transmitter intermodulation, which is to measure the third and the fifth intermodulation products that are caused by the presence of wanted signal and the interfering signal reaching the transmitter via the antenna. For this test setup, a circulator will be used to input the interfering signal to the transmitter and then output the signal for measurement. What is the interfering signal? It's also 5G NR signal with 15 kHz subcarrier spacing, minimum bandwidth on the operating band, and a power level of 30 dB lower than the wanted signal. There are 3 different frequency offsets defined for the interfering signal position, for single or multi-carrier signal, and also within subblock gap for non-contiguous spectrum. The frequency offset is relative to channel edge or subblock edge. Interfering signal and wanted signal frequencies will be excluded from the test. Then what is the pass or fail limit for the intermodulation test? When an intermodulation product appears in a specific frequency range, the emission limit of ACLR or OBUE or spurious emission corresponding to that frequency range will be applied. So the limit masks we discussed in previous slides could be pretty much reused for the intermodulation test. So far, we have discussed all the transmitter test items and seen the measurement examples using N9085EM0E 5G NR measurement application. You may have the question, what hardware platform this application can be running on? Basically, it can support a wide range of Keysight signal analyzer models, as well as the PXI transceivers, from the cost-effective model to middle-range ones and to very high-end ones. Though these analyzer models have different frequency range, analysis bandwidth, and RF performance, the built-in 5G NR application can always give you the consistent user experience, which is a big convenience for sharing the test cases from R&D to verification and to manufacturing. Regarding the test automation, for each parameter on the application GUI, there is a corresponding skipping command available for customer to configure the measurement or query the result in the programming way. That means customer can fully automate the conformance test with those commands. Okay, that is all for today's discussion. Thanks for your attention. If you have any questions, please type it here. Thank you.
Thank you, Peng, for your presentation. Before we get to Q&A session, I'd like to call your attention to our survey, which should be displayed to the right of the slide. If that window is not showing on your console, click the icon in the widget bar at the bottom of your screen. The survey is your chance to tell us a bit more about yourself, what your engineering challenges are, and what we can do to help. We also use your feedback for future topics. Please be sure to fill it out before you leave. Thank you. And now we have a first question here. So the question goes is, can this 5G and R measurement application run on a PC? What licenses or license does it need, and is it possible to get a trial license for evaluation?
No, N9085EM0E NR measurement application is embedded in the firmware, in the instrument firmware, so it can only run on Keysight spectrum analyzers or transceivers. It will need to capture the IQ data from the hardware for analysis. So if you already have those supported instruments in your lab, you can go to keysight.com, find XApps to apply a 1-month free trial license. Or you can contact the local Keysight salesperson for arranging a demo instrument for you. Thank you.
So next question we received in the chat. You mentioned test model preset in the measurement application. What's the supported spec version for test model? And how often will you update it to align 3GPP change?
Okay. The latest XApp 2020 release supports December 2019 version for the test models. We have very close tracking to the 3GPP spec change and also contribute to some test items. Usually, a new software version will be available no later than 3 months after 3GPP spec publish, and beta versions could be even earlier for customers who want to access the new updates. Okay, thank you.
So next question we received, the advanced preset looks like a great feature. Does it support preset for multi-carrier signals?
Yes. Multi-carrier preset is supported, and for both contiguous and non-contiguous cases. It allows you to specify the number of component carriers at the non-contiguous point. So it will make it very easy and flexible to configure the multi-carrier signal with the sub-block gap settings. Thank you.
The following question is, what is the Keysight solution for base station receiver testing?
Just now I mentioned we are planning an advanced session of this webinar to cover some of the receiver testing topics. Basically, we have N7631C Signal Studio software running on a PC with the full coverage and the preset for receiver testing. It can connect to a wide range of Keysight signal generators to play the 5G NR signal. Also, we have the embedded 5G NR signal generation application in VXG signal generator, where user can generate a 5G NR signal through a multi-touch screen or through the skippy command for automation tests. Okay, thank you.
Okay, so I think we have enough time for one more question. In the video, it mentioned preset can cover more than 50 tables. Can you explain what is included in those tables?
Well, I think you are asking about the advanced preset for ACLR, OBUE, and spurious emissions. Generally, those tables are defined in the test spec for different test conditions, and it includes the frequency offset, measurement bandwidth, and pass and fail limit values. So especially if there are multiple segments in the frequency domain, you will find using the preset will be quite convenient for you to finish the configuration. Okay, thank you.
Thank you, Peng, for answering all these questions. So this concludes today's webinar. As a reminder, you will receive an email when the recording becomes available. Before you leave, you can download a copy of the slides now in the resources widget. Once again, thank you to our presenter, Peng, and everyone online for joining us. This webinar was brought to you by Keysight Technologies. You will enjoy your day today. Thank you.